Hello student, today in this video we will study about the semi-empirical mass formula. Now what is a semi-empirical mass formula? It is basically the measurement of factors on which the binding energy of the nucleus depends. In this formula we will derive the formula for the binding energy terms. Like how does the binding energy of the nuclei depends on different factors which are influencing the binding energy of the nuclei. Now what happens inside the nuclei? Let's suppose this is a nucleus. There are some factors which helps in increasing the binding energy. Like if they increase the stability of the nuclei, then they will contribute in binding energy, and if some factors decrease the stability of the nuclei, then they will contribute its role in decreasing the binding energy of the nuclei. So therefore we can understand it as the total binding energy is the combination of both the factors which are increasing the stability and factors which are decreasing the stability of the nuclei. We can describe the binding energy term as a combination of all these terms. The first term is a volume energy term, second is a surface energy term, third is a Coulomb energy term, this is a asymmetry energy term, this is the pairing energy term, and this is the magic number energy term. Now we will define it one by one. Here EV is a volume energy term. Volume energy term, in this volume energy is directly proportional to the A, where A is the number of nucleons. Higher the value of A, more will be the number of nucleons present in the nuclei, and higher will be the pi meson exchange. More the pi meson exchange, more will be the nuclear forces that will come into the picture. So the volume energy term helps in increasing the binding energy, so we will take it as in the positive form, and the expression of AB we must remember, which is a 14.1 MeV. The second term that comes into picture is a surface energy term. Surface energy term consider is in the form of minus of As into A raised to power 2 by 3. Now why it is contributing in the negative form? Now let us suppose this is a nucleus in which the nucleons are present inside the nucleus. In the surface energy term, all the nucleons are present at the surface and they have a larger tendency to escape the surface. Therefore nucleons present at the surface are less stable than the nucleus present inside the nuclei. Therefore the nucleons present on the surface helps in decreasing the stability, just like the surface tension that we have already studied in our lower classes. Therefore surface energy term is directly proportional to the surface area of sphere. So as we know, the surface area of the sphere is 4 pi r square, and we have also studied in our first video where radius of nuclei is directly proportional to A raised to power 1 by 3, and we will put square on both sides and we will get the factor A raised to power 2 by 3. Hence in this way the surface energy term is directly proportional to A raised to power 2 by 3 and with negative sign, and this constant which is known as a surface energy constant, its value is 13.1 MeV that we must kept in our mind. Third is the Coulomb energy term, like Coulomb repulsive energy term. Now let's consider the case of a nuclei having the number of protons which are repelling each other. This repulsion between the proton and proton results to the Coulomb repulsion term. So we can write it as AC is equals to minus of AC Z into Z minus 1 A raised to power 1 by 3. Because in this case the nucleons are also decreasing the stability of the nuclei. Therefore this factor is also decreasing the binding energy, so we will put the negative sign here, and the value of AC that we must kept in our mind is 0.595 MeV. Next factor is a asymmetry energy term. Now let's understand what is asymmetric energy term. Now let's plot a graph between proton number and number of neutrons. There is a case when the number of neutrons and protons are equal, then we say our nuclei is stable. And as we know, as the number of protons increases, as the atomic size increases, the number of protons starts increasing, which results in the repulsion, and to counterbalance this repulsive force, number of neutrons starts increasing in the higher nuclei. Therefore this results in the asymmetry of the energy, and with the increase in the size, the number of nucleons starts increasing, which led to the instability and asymmetry. So this arises due to the Pauli's exclusion principle. Like we can understand in this case, suppose we have energy levels for the boron and for the carbon. Here boron is unstable and carbon is stable. Now let me explain how this is happening. Now in this case, the blue color is representing the protons and red colors are representing the neutrons. We have 5 protons in case of boron. We have in the first energy level with spin up and spin down, we have entered up spin proton and down spin proton in the first level. In the second level, we have also put one proton in up spin and one proton in down spin, and one proton which was left we have put it in the third state. In the case of neutrons, similarly we have also put 2 neutrons with spin up and down in first state, with 2 neutrons with spin and up and down in second state, with 2 neutrons in third state with up and down spin, and third neutron in the fourth state. Now what is happening in the case of carbon? We have 6 protons and 6 neutrons. We have put all the 6 protons in the 3 states with up and down spin, and we have also added the 6 neutrons in the 3 states with a spin up and down state. Now here only 3 states are filled and here 4 states are filled. Since here all the states are fully filled, but in this case fourth state is still partially filled. So this case is the instability case, and we can also find out like the number of protons upon number of neutrons, or number of neutrons upon number of protons are not 1, but in this case number of neutrons upon number of protons is equal to 1. So this factor led to the higher stability and this factor led to the lower stability. So in this way we can understand how this asymmetry energy term comes into picture. This comes into picture only when the number of neutrons are higher than the number of protons. So this factor will reduce the binding energy of the nuclei in the higher atomic number. So the negative sign is added here, and it is due to the number of neutrons are increasing, so we will add the factor a minus 2z square upon of a. This factor we also must keep in our mind. Sometimes examiner may ask you question about the asymmetry energy term, and the value of AA we must also remember, which is 19.0 MeV. The last term that is contributing is a pairing energy term. Now what is happening in the pairing energy term? If we have pairing energy term, then it will be, if suppose if we have a pair of even nuclei, like even number of protons and even number of neutrons, then it would be added, and if we have odd nuclei, then the pairing energy term will be in the negative form, and if we have odd even number of nuclei, then it would be 0, and the value of AP is 33.5 MeV. Last one is a magicity energy term, that which is contributing to the magic number, which is 2, 8, 20, 28, 50, 82 and 126. These are the magic number. If the nuclei contains these number of nucleons, then we will say that it is contributing to the binding energy term in the positive way. So we can combine all the energy terms and write it in this expression, and we must keep it in mind that binding energy term is equal to AB into A, which is contributing to the volume energy term, minus of AS into A raised to power 2 by 3. It is contributing to the surface energy term. Next is the Coulomb energy term, which is contributing to minus of AC into Z minus 1 upon A raised to power 1 by 3. This energy term, which is known as the asymmetry energy term, which is related to the negative binding energy and is minus of A into A minus 2z whole square upon A, and is a pairing energy term which is plus minus or 0 AP upon A raised to power 3 by 4. So this was the total formula for the binding energy term. So this was all about the binding energy term that we have calculated by using the semi-empirical mass formula. If still you have any query, then you can ask me. Now let's move on to our next topic, which is the liquid drop model. What is liquid drop model? It is basically the 3 energy terms that we have already calculated in our semi-empirical mass formula. Like here we will consider the only the 3 energy terms. That is, the first one is a volume energy term, second is a surface energy term, third is a Coulomb energy term. In this volume energy term, which is directly proportional to A, and surface energy is directly proportional to A raised to power 2 by 3 but with negative sign. Coulomb energy term is directly proportional to Z into Z minus 1 upon A raised to power 1 by 3 with minus of AC. Why it is known as a liquid drop model? Because its properties resemble with the drop of a liquid. Suppose if we hit a liquid drop, it splashes. Similarly, if we provide higher energy to nucleus, then it will break it down. We can also understand its graph like this. Suppose this is the binding energy per nucleon and this is the number of nucleons. Here we are considering the first term, which is a volume energy term, which is directly proportional to A. As the number of nucleons is directly proportional to A, it means that it is a volume energy term and it is a higher and it is a positive, so we will write it as in the positive sense. Second is the surface energy term. In the surface energy term, as we know, for the lower value of A, more the nucleons are present on the surface, but with the increasing value of A, nucleons present on the surface are less than the nucleons present inside the core, therefore the surface energy term starts decreasing. And third one is the Coulomb energy term, which is inversely proportional to A. Like as the A increases, then the binding energy per nucleon it starts decreasing, so this is the curve in this direction. Now the total energy term will be the summation of this curve and the volume energy term, so it is the total energy curve. I think you have understood the liquid drop model. It is a very easy and very similar to that of the semi-empirical mass formula. We just need to take the first three energy terms. How does the question come from this concept? Suppose if the value of A for a nuclei A1 is 50 and that for the nuclei B1 is 60, then calculate the value of ratio of volume in binding energy term. In this case, the examiner may ask about the volume binding energy term, so we will consider only the EV term. It is for the first nuclei and EV term for the second nuclei. For first term, the value of A is 50 and for the second nuclei, the value of A is 60. So we can cancel out AB by AB and we will get 50 upon 60, so which is equals to 5:6. So this is our answer. Similarly, you can also solve for the surface energy term or the Coulomb energy term. In this way, the examiner may ask about any energy term or about the total binding energy term. I think you have grasped all the concept till here. Now let's move on to the important formula. In the NET exam and in many competitive exams, examiner always ask about the most stable isobar. Now just remind, what are the isobars? Isobars are those nuclei having Z is variable and A is constant. You can also learn this concept like bar. When we write a bar of any object, we will write it in the form of X bar. Like we will put the bar on the upper side. Bar on the upper side means upper side nuclei. Like we will always write A on the upper side. We will take it as a constant and we will vary the lower term like Z. We will vary the Z as in the nuclei. Now we need to calculate the value of most stable isobar. First of all, we need to know about the binding energy term that we have calculated here, this term. Now we need to calculate the stable isobar. For the stable isobar, we need to calculate the constant value of Z, for which variation of EV by EZ is equals to 0. Means we need to take the derivative of EV term with respect to Z, so to calculate the stable value of Z. So for this we will partially take the derivative of this binding energy term with respect to Z and we will substitute it equal to 0, and we do not need to calculate it here. We just need to memorize this formula. In the CSIR NET exam, one question was asked in December 2015 in which A was given, AC was given and AA was given. We need to calculate the value of Z. We just put all these values in our previous formula and we'll get the answer 52. The next question that once was asked in June 2016, that ES denotes the contribution of surface energy term per nucleon in the liquid drop model. Now as we know, the surface energy term is directly proportional to A raised to power 2 by 3, but he was asking about the surface energy term per nucleon, so we need to divide it by A and solve the question. Now our next topic of discussion is the different types of decays. Now why does a decay occur in a radioactive element? Look, decay occurs only in the case when the nucleus is not stable. It occurs because of the instability of a nuclei. First case is larger the size of nuclei, more will be the proton-proton repulsion, and higher the proton-proton repulsion, more will be the instability of the nuclei. And because every every second person or every second body in this whole universe wants to be stable. So to get that stability, it undergoes a process which is known as a decay, in which some energy is emitted or some particle is emitted from a nuclei to get smaller. So a larger size nuclei becomes smaller and becomes stable by undergoing a process which is known as a decay process. Now there are different types of decay: alpha decay, beta decay, gamma decay, positron emission decay, orbital electron capture, and Auger electron. We will discuss all these one by one. First of all, we will study about the alpha decay. Now why does the alpha decay occurs? Alpha decay occurs because of the size of the nuclei is very big. When the size of nuclei starts increasing, then the protons and neutrons becomes very much higher in number inside the nuclei, that the protons starts repelling each other, and the nuclei becomes so unstable that it undergoes a decay. It emits one particle which is known as a helium particle, and this process is known as a alpha decay because helium particle is known as a alpha particle. So it undergoes a smaller nuclei and it becomes stable. So this is the alpha decay. Now what is exactly happened? Suppose this is our nuclei which is represented by ZXA, and by emitting alpha particle which is 2He4, it results to give Z minus 2 into Ya raised to power minus 4, which is a daughter nuclei. We can also understand it in this form by the case of the uranium 92-238, it undergoes alpha decay and results to give a thorium 90-34. So to calculate the kinetic energy of the alpha particle, we must remember this formula, which is A minus 4 upon A into Q. What is Q here? Q is the energy that is related to mass of parent nuclei minus mass of daughter nuclei plus mass of alpha particle into c square. And if we need to calculate the kinetic energy of the daughter nuclei, it is 4 by A into Q. That we must keep in our mind. And when we will talk about the kinetic energy of the alpha particle, it is always A minus 4 upon A into Q. And when we will talk about the kinetic energy of the daughter nuclei, it will always be 4 upon A into of Q. Now sometimes the question asks about the radioactive branching. Now what is radioactive branching? Suppose we have a sample of radioactive nuclei. Some of the nuclei it undergoes alpha decay and some of the nuclei it undergoes beta decay, and this is known as a radioactive branching. So in the alpha decay, we will get to know the kinetic energy of the alpha particle would be this one, and the kinetic energy of the daughter nuclei, which is this thorium, is 4 upon A into of Q. Now how to calculate Q? We will calculate the mass of the parent nuclei minus mass of daughter plus mass of the alpha particle into of c square. So this is how we can calculate the value of this Q. Now what is the range in alpha particle? It is basically the nuclei from which it emits. Suppose alpha particle generated here, and after traveling a distance r it stops at this point, then this distance is known as a range of the alpha particle. Now what is happening during this process, that like from emitting to stopping, it interacts with many particles. Alpha particle starts interacting with many particles, then it will show the ionization. The distance it traveled, that is from the point it emits and the point it gets stopped, is known as a range, and the value of the ranges varies from 2.7 cm to 8.6 cm. Sometimes question might be asked from this. Range depends upon the decay constant which is related to this equation, like log of lambda is equal to a plus b into log of r. Now range depends also on the temperature of the alpha particle. Higher the value of the temperature, higher would be the range of the alpha particle. As the temperature increases, the alpha particle have the thermal kinetic energy, then the range of the particle becomes higher. Range also depends upon the pressure. As the pressure increases, range starts decreasing. Now why it is happening? Let's suppose that there are a number of particles present outside the nuclei. When the alpha particle starts emitting and when the pressure starts increasing, the particles of the medium, they are more dense in more surrounded towards the nuclei, and it would be very difficult for alpha particle to move from these particles or to pass through from these particles. So pressure of the medium particles add obstruction in the path of the alpha particle, so it reduces the range of these alpha particle. We must also know what is a alpha particle. It is a helium nuclei having 2 neutrons and 2 protons. Since it is a helium nuclei, so its size is very much appreciable, which helps in reducing the size of the nuclei. Another important property is the penetration power of alpha particle is very small because of its bigger size in comparison to the beta and gamma rays. Ionization power is very higher than that of beta and gamma rays. Effect on the photographic plate is less, and it shows up properties of fluorescence also. Now we will discuss about what is a beta decay and why it is happening. First we will study why it is happening. It is because when a nuclei having the number of neutrons greater than that of the number of protons, then the neutron starts decaying and it will undergo a beta decay. We can understand it is in this form. There is a neutron which is attached to a nuclei. It will undergo a beta decay in which it emits electron, and with electron it will also emit an electron antineutrino. Why this is also emitting with this is because to conserve the spin of this interaction. Since this process is occurring inside the nucleus but electrons are emitted, as we know electrons could not stay inside the nucleus, so electrons move out of the nucleus and is known as a beta ray emission. Do you understand what is happening? In the case of this beta decay, electrons are emitted, but whole this process is occurring inside the nucleus, but also we know electrons can't reside inside the nucleus, therefore these electrons come out of the nuclei and this decay is known as a beta ray emission. Now what is gamma decay? When the nucleus carry excess amount of energy and to become stable it emits excess energy and is known as a gamma radiation, and this energy that emits in the form of radiation is known as a gamma radiation. Now what are the properties of gamma decay? The gamma rays are electromagnetic radiations. Gamma rays do not change z or n. When the gamma rays are emitted, the atomic number remains same and the number of neutrons remains same, but difference is just like it goes from excited to the ground state and with the emission of some energy. What is happening actually inside the gamma decay? Excited state nuclei converts into ground state nuclei with the emission of some energy. Now the question might be arise like this one: which phenomena will take place when nuclei carry excess amount of energy? Then the gamma decay is there. Now the next question: during gamma decay, how A and Z varies? First is A increases, Z decreases, A decreases, Z increases. Both A and Z increases, A and Z remains same. So the answer would be A and Z remains same, because in the gamma decay only excited state nuclei comes to their ground state with the emission of some energy. Now the next concept is electron capture. Now why this electron capture is happening? If the nucleus has a higher number of protons than the number of neutrons, then what is happening? The orbital electron is captured by a proton. Suppose this is a nucleus and they are containing large number of protons and lesser number of neutrons. Then electrons are revolving around in this form. Proton being higher in number, they will capture one electron here and would results to become another nuclei, and this process is known as the electron capture. Now what is happening in the case of positron emission? If inside the nucleus number of protons are still greater than the number of neutrons, now what will happen? It will generate a positron with a neutrino. This is known as a positron emission. So this is for today.